Every kilometer of this road hides thousands of tires that once raced down highways, now completely unrecognizable. Each year, more than 1.5 billion used tires are thrown away, and they're among the hardest materials on Earth to dispose of. But in the United States, those tires aren't going to landfills. They're being crushed, blended into asphalt, and reborn as modern roadways. What looks like ordinary black pavement is anything but ordinary. Beneath it lies a complex feat of engineering. Subscribe to uncover how it all works. So how do discarded tires become the foundation of smoother, stronger, and more durable roads? Let's dive in. From tire waste to road revolution. The world discards more than 1.5 billion tires each year, a number so enormous that from the air, storage sites look like dark oceans stretching to the horizon. When left in the environment, tires barely break down, slowly leaking harmful chemicals and turning parts of the United States, Europe, and the Middle East into major pollution hotspots. Yet this overwhelming waste has sparked an unexpected shift. Rubberized asphalt has grown into a multi-billion-dollar industry. Just 1 kilometer of road can reuse up to 10,000 tires, creating surfaces that last longer, resist cracking, and reduce traffic noise by nearly 6 decibels. Once a symbol of pollution, discarded tires are now emerging as promising construction materials in practice today. Tire collection and recycling process. Each day, within the quiet rhythm of modern cities, thousands of vehicle tires reach the end of their service life at garages, maintenance stations, scrapyards, and large tire replacement centers. Most have exceeded safe limits for tread depth, elasticity, and load-bearing strength, making continued use impossible. When abandoned in nature, a single tire can persist for decades with almost no decomposition. Over time, it releases organic compounds and heavy metals, becoming a long-term source of contamination for soil and groundwater. In many countries, a worn tire is worth only a few cents as scrap, yet to recyclers, it represents urban ore. Inside every tire exists a complex mix of natural rubber, synthetic rubber, reinforcing steel, textile fibers, and chemical additives. When processed correctly, these materials can be recovered and reused with significant economic value rather than lost to waste. Collection is organized along fixed routes. Specialized trucks with reinforced platforms and secure fastening systems gather tires from multiple sites to reach efficient transport volumes. This method lowers logistical costs and prevents outdoor storage where tires can trap rainwater and become breeding grounds for disease-carrying insects. Recycling begins with the steel reinforcement. This steel ring locks the tire firmly to the wheel rim at high speeds, but inside a recycling line it becomes an obstacle. If left in place, it can damage cutting blades, break drive shafts, and shut down shredding systems. At the first stage, workers feed tires into bead removal machines. Hydraulic hook mechanisms generate pulling force, digging deep into the tire bead and extracting the steel core in seconds. The force is intense enough to twist and deform thick rubber bodies. Each heavy-duty truck tire yields about 2 kilograms of high-quality carbon steel. Once separated, steel wires are gathered, compressed into bundles, and transported to metallurgical plants, beginning a new life cycle. The remaining tire carcass moves forward. Before cutting begins, it passes through high-pressure washing systems that remove mud, oil residue, and embedded gravel. This step protects cutting equipment from premature wear and ensures stable operation downstream. In primary shredding, whole tires enter high-torque machines where slowly rotating alloy steel blades slice them into coarse fragments. Low-speed cutting minimizes heat, preventing rubber from softening or sticking while preparing material for further processing. Secondary grinding reduces fragment size further while mechanically fracturing remaining steel. Magnetic systems recover this metal directly from the flow, creating another recyclable stream. The final output is crumb rubber with controlled particle size. At this stage, the tire has lost recognizable form and becomes raw material for uses in construction, transportation, and manufacturing. At the end of the line, classification screens separate particles by size. Material meeting specifications moves forward, while larger pieces return for regrinding. The critical fraction between 0.5 and 2 millimeters is reserved for rubberized asphalt, the focus of what comes next. This entire process transforms discarded tires into standardized material ready for controlled industrial reuse applications. Before we dive into the production process, subscribe for more hidden engineering stories. Rubberized asphalt production process. After crushing and screening, crumb rubber from waste tires still holds residual moisture, fine dust, and traces of embedded impurities. These elements interfere with how rubber interacts with hot bitumen, limiting bonding strength and preventing the stability required for high-performance pavement. Before blending into asphalt, crumb rubber must pass through a dedicated drying and heating stage. Inside the plant, rubber granules are fed into a rotating drying drum, a large steel cylinder set on a slight incline and kept in constant motion. Hot air, produced by burners fueled with natural gas or fuel oil, flows through the drum at temperatures between 200 and 260 degrees Fahrenheit. As the material tumbles, moisture is gradually removed and the surface of each rubber particle becomes dry and chemically active, ready for interaction with bitumen. Modern production lines tightly control this stage using temperature sensors and airflow regulation to prevent scorching or loss of elasticity. Many facilities rely on indirect heating, keeping rubber isolated from direct flame to preserve internal polymer structure. Once properly conditioned, the rubber enters the blending phase where its transformation accelerates. Bitumen is heated separately in storage tanks until it reaches a stable liquid state, typically between 320 and 375 degrees Fahrenheit, ensuring smooth flow without chemical degradation. Crumb rubber is introduced into the mixing chamber in carefully measured amounts, usually between 10 and 20% of total binder mass, depending on formulation requirements. Inside the mixer, heat-resistant paddles create a continuous vortex, forcing rubber and bitumen into sustained contact for 30 to 60 minutes. During this period, rubber particles swell as they absorb lighter oils from the bitumen. This increases mixture viscosity while greatly improving elasticity and resistance to cracking. These properties are critical for road surfaces exposed to heavy traffic loads and repeated temperature fluctuations. Throughout blending, modern asphalt plants monitor viscosity, temperature, and residence time to ensure uniform rubber distribution and prevent clumping. Some systems also add stabilizing agents to reduce phase separation during storage or transport. By the end of blending, rubberized asphalt reaches a homogeneous, stable state ready for asphalt concrete production, where discarded tires officially become part of resilient road infrastructure. Immediately after blending, the hot mixture is discharged into specialized dump trucks with preheated beds to prevent sticking or premature cooling. Loading temperatures are maintained between 270 and 300 degrees Fahrenheit to preserve workability. Each truck then follows a planned route toward prepared job sites, carrying recycled tires toward their final roll beneath American roads. Laying the road, modern asphalt paving. Now comes the most critical stage of highway construction: laying the asphalt. Across the United States, paving technology that incorporates rubber from recycled tires has evolved far beyond earlier methods, turning what was once a slow, layered process into a precise, highly controlled operation. Dump trucks arrive carrying hot asphalt maintained at roughly 160 degrees Celsius and unload it directly into the paver's hopper. From there, conveyor belts and augers move the material steadily toward the rear, ensuring the mix is distributed evenly across the full width of the roadway. The key action takes place at the screed, the vibrating tamping and pressing unit positioned at the back of the paver. While the asphalt is still extremely hot, the screed can achieve between 85 and 92% compaction. This allows the layer to be shaped, compressed, and smoothed in a single pass, setting the foundation for long-term performance. This approach is especially effective for surface courses such as stone mastic asphalt, which are typically only 2 to 3 centimeters thick and cool very quickly. Traditional vibratory rollers used on such thin layers can create cracks or ripples. Modern automatic screeds avoid this problem, producing a surface that remains smooth, evenly textured, and uniform along the entire stretch of road. In earlier decades, crews relied on multiple rollers, vibratory, static, and pneumatic, to reach proper density. Today, advanced asphalt pavers perform more than half of the compaction internally, reducing reliance on heavy roller passes. Vogela pavers from the Wirtgen Group are widely recognized for their precision, material efficiency, and ability to reduce roller work by 70 to 80% compared to older techniques. After paving, a light steel roller may complete a final pass, though many projects skip this step because the surface already meets specifications directly out of the machine. Modern paving systems also combine bonding and placement into a single operation. As the paver moves forward, front nozzles spray a thin tack onto the existing pavement. This bonding layer acts as adhesive, preventing slippage under heavy traffic. Immediately behind the spray bar, the recycled asphalt mix is placed without delay. The screed spreads, vibrates, and compacts the material continuously, forming a durable, uniform surface designed to withstand years of constant use. Finishing the highway system. Once the asphalt cools and reaches full stability, the next phase begins, guiding traffic safely across the new surface. Crews first mark out the layout using laser measuring tools or guide strings, defining the exact placement of lane lines, dividers, stop lines, and directional markings with precise accuracy. With the layout confirmed, a specialized striping machine moves into position. It applies thermoplastic reflective paint heated to roughly 180 to 200 degrees Celsius, allowing the material to bond tightly with the asphalt. As the spray head advances, it lays lines with exact width and thickness required by highway standards. At the same time, glass beads are released onto the fresh paint. These beads reflect headlights at night, dramatically improving visibility and reducing accident risk. Within minutes, the markings cool, harden, and lock into the pavement. The roadway surface is now visually complete and ready to support traffic flow. The next step focuses on physical protection. Concrete barriers are installed to manage traffic and enhance safety. These barriers are typically precast in factories before being transported to the site. There, concrete is poured into high-precision steel molds to ensure uniform dimensions and angles. Vibrating tables compact the mix, increasing density, strength, and surface smoothness. After curing, each barrier is removed, inspected, and numbered according to its installation sequence. At the construction site, cranes or specialized forklifts place each segment exactly as specified in the engineering plans. Workers connect them using steel pins or bonding adhesives, forming a continuous and stable barrier system. This precast approach accelerates construction, minimizes road closures, and improves worker safety. With barriers in place, engineers carry out a final inspection of the entire highway. They evaluate surface smoothness, drainage, traction, and structural integrity across every section. Only when all components meet strict technical and safety standards is the highway officially approved and opened for use, completing its transformation into a fully operational transportation system. And so, what was once hazardous waste has been crushed, recycled, and woven into modern transportation. Beneath the smooth black asphalt millions drive over daily lies a story of engineering, environment, and smart recycling. This information comes from multiple sources. Share corrections if needed. If this journey intrigued you, hit like, subscribe, and comment your thoughts below.